So for this video, we are tasked to solve this linear system using Gaussian elimination. In short, we need to come up with our row echelon form after the application of row operations to the equivalent augmented matrix of this linear system. So we are going to start with this linear augmented matrix here. Okay, using the coefficients, we have 1, negative 1, 2, negative 1, and then negative 1. For the second row, 2, 1, negative 2, negative 2, and another negative 2. Then negative 1, 2, negative 4, 1, and 1. Then 3, 0. We don't have y nor z, so 0. For the fourth row, negative 3, and negative 3. So again, our goal here is to come up with a row echelon form using the Gaussian elimination. And we are going to check what would be the values of the variables x, y, z, and w, if there are any. So to do this, of course, our first entry on the first row is already 1, so we don't need to apply any other operations for row 1 to change it. But we can apply operations to row 1 and subject the results to row 2, 3, and 4 to make these 3 entries 0 as a requirement for our row echelon form. And these are the operations. We're going to multiply negative 2 to row 1, add it to row 2 for a new row 2. That's for the new row 2. For the new row 3, simply add row 1 and row 3 to have a new row 3, because 1 plus negative 1 will be 0. And finally, for our fourth row, multiply negative 3 to row 1, add it to row 4 to have a new row 4. So let's apply all of these operations here, and this might take long, so I still have spaces at the bottom. So again, the first row is still as it is, 1, negative 1, 2, negative 1, negative 1. And then for the first operation, negative 2 times 1 is negative 2 plus 2, 0. Next, negative 2 times negative 1 is positive 2 plus 1, that's 3. Negative 2 times 2 is negative 4 plus negative 2 is negative 6. Negative 2 times negative 1 is positive 2 plus negative 2, that's 0. Negative 2 times negative 1 is positive 2 plus negative 2, also 0. So that's for our second row. For our third row, simply add row 1 and row 3. 1 plus negative 1, 0. Negative 1 plus 2 is positive 1. 2 plus negative 4 is negative 2. Negative 1 plus 1, 0. Negative 1 plus 1, 0. Then, let us have this next. Negative 3 times 1 is negative 3 plus 3, 0. And we have achieved this. That's our goal earlier. And apply for the rest. Negative 3 times negative 1 is positive 3 plus 0. So we have positive 3. Negative 3 times 2 is negative 6 plus 0, negative 6. Negative 3 times negative 1 is positive 3 plus negative 3, 0. Negative 3 times negative 1 is positive 3 plus negative 3, 0. Okay, we observe that the second row and the fourth row are of the same coefficients, and the third row is this, actually a multiple of, or the second and the fourth row are multiples of the third row. So you might see some unique relationships here, but let's make this first a leading one. So let's multiply 1/3 to all the entries of row 2 for a new row 2. Okay, and then let's do it first. We could of course try to inject other operations to make these zeros here, but since it might be with a lot of fractions, so let's just do this with this operation alone. So you have 1, negative 1, 2, negative 1, negative 1. Either way, if it is actually given that as long as you're doing it right, all row operations will result to the same row echelon form or reduced row echelon form, and they will have the same results. So it doesn't matter what operations you're focused on or what scalar quantities you're multiplying to each specific row. Anyway, so divide second row by, or multiply second row by 1/3, that's 1. This is -2, 0, 0, 0, 1, -2. We did not apply anything to the third nor the fourth row. So we are going to apply it here now to make these 2 zeros here. So we'll have -1 times row 2 plus row 3 to have a new row 3. And then -3 times row 2 plus row 4 to have a new row 4. And see what will happen here. The first row is still as it is. The second row is 0, 1, -2, 0, 0. But the third and the fourth row will look like this. Okay, -1 times 1 is -1 plus 1, 0. Of course, this is 0 here. -1 times -2 is +2 times -2 is 0. -1 times 0 times 0 plus 0 plus 0, so 0. The entire third row is a row of zeros. Check what will happen to the fourth row. -3 times 1 is -3 plus 3 is 0. Of course, this is 0 here as well. -3 times -2 is +6 times -6 is 0. -3 times 0 plus 0 plus 0, 0, 0. So both of our third and fourth rows are rows of zeros. This would mean this is already our end of our Gaussian elimination, as we have achieved our row echelon form. And noticeably, we have 2 non-zero rows, this first row and second row. But earlier we have 4 variables, x, y, z, and w. So we will expect here 3 variables, 2 of which there are 2, 4 minus 2, so there are 2 variables that will be represented by arbitrary variables. In short, this is an example of a linear system with infinitely many solutions. So to compare this to our original linear system, let me copy here so we would know that these are the coefficients. Let me copy this final row echelon form here. So 1, -1, 2, -1, -1. Our second row is 0. So that's 0, +1, -2, 0, 0. And the third and fourth rows are all 0. So with this, we could come up with these equations. X minus y plus 2z minus w is -1. And the second, we'll have here y minus 2z is equal to 0. We don't have any other variables for or other equations that will include x and w. So we will expect that they will be, of course, we will expect that there are representations of arbitrary variables here. But let's start with w. Okay, so let w be t. Okay, that would mean this is already with a representation. But to address the second equation of y minus 2z, let's also use z as equal to s. So there are 2, again, as mentioned, 2 variables represented by our arbitrary values t and s. So with this second equation will become y minus 2z, which is 2s, equal to 0. And we can solve y in terms of s. Y is 2s. And finally, for our first equation, you will have x minus y, which is 2s, plus 2z. So 2z is s as well. And then minus w, which is t, equal to -1. So we could have it, this is of course 0. So x is now equal to -1 plus t. This is our representation for our x. So these are now the representation, because we don't have exact values, for the variables x, y, z, and w. We have infinitely many solutions depending on the values that you're going to use for s and t, arbitrary variables. And this is the solution for this linear system using Gaussian elimination. Thank you for watching.